It takes time to transition. Some encryption transitions takes like 5 to 10 years, so it's important to be doing that now, and also show not only the urgency within the government system to transition, but as well as private companies who probably don't know much about quantum computing in some cases and don't know about this risk. There's, I think, a lot of work that could be done by the US government to sort of display that urgency and display the need to transition to audiences that might not know about it.
Yeah, I absolutely agree with that. I agree with you both that the US government has done quite a good job through NIST in developing this post-quantum cryptography and setting out clear timelines for when the government should adopt it. And I also agree with you that I think, yes, the kind of biggest action item for the government moving forward is continuing to message the importance of this, because this is a pretty esoteric and little-known topic, but it's a very important one. You mentioned other countries, so how would you say the United States stacks up to the competition, both friendly countries and maybe less friendly ones?
Yeah, that's a good question. So like I said, quantum computing is still in this R&D stage, so competition is an important topic to sort of stay close to because the technology is still shaping, and the first person to build this quantum computer, or first nation to build this quantum computer, of course, had its advantages for these economic advantages of solving problems that have this economic advantage, but as well as the national security implications that we've talked about with encryption and whatnot. It's a really interesting space because I think we're sort of seeing how different approaches to innovation and research play out. I mean, comparing US and China specifically, like China has just a fundamentally different approach where it's a more centralized, state-driven, top-down funding approach. There was reportedly $15 billion that came from the Chinese government invested in quantum technologies. So it's definitely coming from top down, whereas in the US, of course, it's a more vibrant and sort of diverse ecosystem. We have startups, universities, large tech companies, national labs funded by different mechanisms like venture capital, tech companies funding themselves, more sort of focused but decentralized funding from the US government from places like DARPA, NSF, DOE. So you kind of see the two different distinct ways of doing this, and historically, our approach of innovation has proven to be successful, and we believe it will be in quantum computing as well. But the competition is super real. As an example, in 2019, this was sort of from Google, our first big public announcement, where we announced that a quantum computer can actually outperform a classical computer on a certain algorithmic task. And very shortly after, we saw that the Chinese government published a very similar result. So the competition is definitely there. I will say from our perspective, the US is leading in quantum computing specifically, and our tech companies as well as national labs and whatnot have really set the standard in qubit performance and quality and algorithmic performance, and sort of are setting the timelines for quantum computing advancement. Although that's not the full scope of all quantum technologies that exist, taking advantage of the China's approach of this sort of top-down system, they're able to excel in areas like something called quantum communication, where they're able to set up these quantum networks at a state level, so they can excel in areas like that. But it's a very critical time for quantum computing because the technology is sort of taking shape, and there's a lot of discoveries to be had. Something I could have mentioned in the introduction to quantum computing, there's different ways you can build these qubits. So another area where the US leads is because of our diversity, we have diverse approaches to building qubits. And there's not really one clear winner for the approach to these qubits, so it's really important to continue to invest in all of these different approaches to kind of see which one is most beneficial. They each sort of have their pros and cons, so making sure that we're investing in all of them is super important. And I think just making sure we continue to maintain or at least accelerate the general health of the US R&D ecosystem to make sure that we're able to innovate as quickly as possible.
Yeah, I also agree with all of those points as well. I'll just mention, I'll plug one of my own reports. I wrote a long report comparing the US and China in quantum technology. It's available for free on RAND's website in case anyone wants to check it out.
It's very good.
But thank you. But yeah, I mean, the highlights are exactly what Elizabeth just said. It's across all of quantum, it's kind of a nuanced story. There are other quantum technologies beyond quantum computing, some of which China does lead the US in. There's arguments about how important those technologies are. That's something we could go into the Q&A perhaps if people are interested. I'll just say in quantum computing specifically, if I could just go into a tiny bit of technical detail, it's an interesting story because as Elizabeth mentioned, there's maybe 6 or so main technical pathways that people are pursuing toward quantum computing. I would say the United States is very strong in all of them, or 5 of the 6 perhaps. Definitely has the broadest range of investment. China's, based on public information, which may or may not be the full story, has a much narrower focus. They're kind of putting all their eggs in one basket, something called superconducting transmon qubits, which actually happens to be the same approach that Google is taking. So I guess imitation is the sincerest form of flattery. And in that particular approach, I would say they're actually pretty narrowly behind the United States. And that is one of the leading approaches. So you can kind of frame this in 2 different ways. You can kind of look at this and say, well, in 5 out of the 6 different technical approaches, the US is very far ahead, so the US is in a quite good place. But you could also frame it as, well, in one of those leading approaches, China is very, very narrowly behind the United States, and they seem to be very fast followers. So with that framing, you could say, well, maybe China's actually pretty narrowly behind the United States. And I think kind of either of those 2 interpretations is defensible. It's like a Schrodinger's cat situation, maybe. Sorry, it's the only physics joke. Didn't land.
It landed for me, I liked it.
All right, so that's kind of, what are quantum computers? What will they do? Where are various countries? What are the risks? Now we'll take 5 more minutes to shift a little bit more toward government policy questions. I'll just say from my perspective, having worked in policy in quantum for several years, the kind of hot topics over the past few years have been export controls, supply chains, and foreign talent. So I'll just kind of toss all 3 of those to you, and you can take any or all of them as you want.
Yeah, I'll try to take all of them. So on export controls, I'll say most generally on each of these points and on quantum policy in general, I think like the most important thing, it sounds somewhat cheesy, is to work together. It's very important for those who are in legislation and creating these policies to be working very, very closely with the industry players that are actually building the technology so that they can actually understand like what goes into this, where are the risks, and how can we help what's happening. On export controls, that definitely remains true. It's super important that we work together with the Department of Commerce and other agencies to make sure that we're developing export controls that, of course, protect our national security, but do not slow down our innovation. We've seen some really good progress in this area and examples of this already. The most recent export controls from the Department of Commerce has, for example, like showed the importance of foreign talent in those controls. So by exempting these controls on foreign talent from the deemed export list, we're able to sort of continue to hire the best talent globally while making sure the rest of our controls are appropriate to maintain national security. So continuing to work together on that is super important. I think like the main areas in export controls going forward that I think could be beneficial is one, being pretty narrowly tailored to specific risks and specific end uses. I think it's not beneficial to have general export controls at this point in time, being that the technology is still taking shape and we're exploring different research areas. I think to that point, making sure that export controls don't favor one type of qubit architecture versus another one, making sure that it's an even playing field for innovation, and even on that point as well is making sure that it's multilateral. So we want to make sure that, the US isn't hindered on certain controls that like-minded countries are not, and we're not just like sort of exporting what our talent and information could be, and we want to keep it here and make sure it's easy and effective to do in the US. Supply chain, I think, was the next one. This is a very complex and important topic. For context, a current single quantum computer has like well over tens of thousands of components, and our larger scale systems will have well over hundreds of thousands of components. So you can imagine that there's a complex supply chain needed to aid that. At Google, we're super proud that we fabricate our own chips and processors in the US in our fabrication labs in Santa Barbara, California, and all of our quantum hardware is developed there. But there's more beyond just the processors. To develop a full system, we do rely on global partners, and there's a lot of very sort of niche and complex things that we need for a quantum computer. There are parts of wiring or these dilution refrigerators and cryogenics that have very few and limited global suppliers. So making sure that we invest in a supply chain that is robust now, but also when we have these larger scale systems is super important. I think the approach is somewhat similar to export controls, where we want to recognize that we want to protect our national security and protect the sort of innovation in the US by investing in domestic supply chains, so bolstering our manufacturing as much as we can here, but also recognizing that we can't onshore, and we probably don't want to onshore every single component. So making sure we have strategic relationships globally with like-minded countries, and there aren't any barriers to limit trade in quantum technologies with like-minded countries. Foreign talent, I sort of touched on a bit before, but this is super, super important. I mean, again, being that quantum computing is at a research stage, it's like our minds that are really the power behind our developments. So making sure that we have the best foreign talent and talent overall, and making sure that a place like Google and in the US is seen as the top place to work on quantum computing is super important. And I think, of course, assuming that the correct security protocols are established, which is another conversation, seeing foreign talent as not a national security risk rather than not having foreign talent is the national security risk. So making sure we sort of take that approach going forward and make the US and our tech companies a desirable place to work and live.
Yeah, I'll just add a couple comments building on that for kind of background for some people in the audience. One is regarding the export controls and supply chains. Having worked on this with government quite a bit, it's a very challenging topic for a reason that Elizabeth touched on, which is there's a lot of different technical approaches to quantum computing that are all being pursued in parallel by different companies, different researchers, different types of qubits, which operate on very different principles. No one really knows which one's going to win in the long run. So I think everyone has to kind of keep a very diversified portfolio. But the challenge is these different technical approaches have extremely different supply chains and extremely different critical components. So just as a concrete example, Elizabeth mentioned dilution refrigerators. One of the most difficult technical aspects to the pursuit that the approach that Google is taking is cryogenics, refrigeration. Their chips need to operate at about 1,000th of a degree above absolute zero in order to work. So refrigeration is a huge bottleneck. There's a lot of extremely esoteric components going into that. Other types of quantum computers operate at room temperature and don't require any refrigeration whatsoever. So for those approaches, dilution refrigerators are useless. And no one really knows which approach is going to win. So we need to keep just a very broad, complicated, and ever-changing landscape of critical components, which is just not easy for anyone to do, even just at the purely technical level, before you get into all the policy complexities of navigating export controls. And the other comment I'll make about the foreign talent is we looked into this as well in our report, and quantum computing, quantum technology in general is sort of an unusually internationally collaborative research enterprise. It's definitely not the case that all the top talent is in the United States or in any other one country. There isn't really any single country that has like a monopoly on the talent here. A lot of the graduate students are international who are like really advancing the field here. A lot of complicated questions around visas and who is allowed to stay in this country. But I'll just kind of throw out the factoid that more than half of all scientific research papers in quantum technology are co-authored by researchers from different countries. So this is like a really international, tightly connected global research enterprise. So I think it just really would not be possible for the United States to go it alone and win in this competition because there's just so much critically important talent scattered throughout the world.
Yeah.
All right, with that, we'll turn it over to Q&A for the last few minutes and then wrap up. And if I could ask people to wait for the microphone before asking the question.
All right. Drew Clark, Broadband Breakfast. You just touched extremely briefly on quantum communication or quantum transport. Could you just help me understand what that is and what's its connection to quantum computing? Is it just basically the ability to transmit lots and lots of capacity, or are there different kind of tools needed beyond fiber optics to make use of the communications that you would use with quantum computing?
Yeah, I can kick it off and then pass it to you. You probably actually know more about quantum communication because Google is a quantum computing effort. But to sort of distill the entire landscape, you can kind of think of quantum technology as the umbrella term. And most generally, it's like taking advantage of these quantum physics principles like superposition, entanglement, and so on to do new things. So in the computing landscape, it's able to process and store information in different ways. In quantum communication, it allows you to communicate information in different ways, also taking advantage of this idea of superposition where you can sort of like simultaneously exchange information, simplistically saying like faster than you ever could before. But I'll let you touch on some of the components that it takes to achieve something like that.
Yeah, it's a big topic. I'll just make a couple points. One is, in terms of the actual components, I would say the links themselves are basically just fiber optic cable for the most part. You can use commercial fiber. It's not actually ideal. It's better to use custom fiber, but people mostly talk about using commercial fiber because it's already there and it does work. But the endpoint devices are very, very different from standard communications. You need single photon sources, single photon detectors. Things are just not very standard. So there are very high hardware costs and a lot of new infrastructure that would need to be employed. The one other thing I'll say very quickly is there's kind of two different paradigms for quantum communication. There's long range and there's short range. So with long range, we're talking about like city scale, national scale. People sometimes talk about a quantum internet. Frankly, I think there's not a whole lot of clarity on exactly what the use case would be there. The other kind of big approach to quantum communications is a shorter range, which is more like a data center scale, where kind of everything is in one very big building. And there, the main application is scaling up quantum computers, having sort of modular quantum computers with multiple quantum processing units, all working in parallel. Conceptually, somewhat similar to a conventional data center. And then I'll just briefly say one application of the long distance paradigm is actually information security and security against eavesdropping and hacking. That's a long topic that's maybe best discussed afterward, but there's a lot to say about that.
Yeah.
Very, very enlightening presentation. You've spent a good deal of time talking about how quantum could crack encryption, today's encryption, and there was an optimism that quantum will develop new forms of encryption that we can use in the future. But our adversaries have spent decades hacking into our systems, government and private sector, to grab encrypted files that are sitting on hard drives in Beijing and Moscow. And I'm wondering whether they will be able to decrypt virtually everything they've gathered and taken from our systems, and what risk that possesses, because I don't think that we can grab those files back once they've got them in hand.
Yeah, I mean, you're touching on a couple main risks in this space, and there are sort of several to think about. One that you're touching on is something we call the harvest now, decrypt later, which is the idea that right now, you could harvest information and not be able to to decrypt it until you have a quantum computer. But in, let's say, 5 to 10 years, you have a quantum computer, you can decrypt that information and you have access to all of that information. So another reason to push for urgency to transition now versus when the quantum computer actually exists, there is risk currently right now. Another thing you sort of touched on is that, like, a lot of the current encryption has been tested for years and years and years, and when developing new encryption standards, we don't have as much time to sort of test those frameworks. So NIST has done a really good job of setting up a space where that can happen, and there's been a lot of amazing minds going towards trying to hack the new standards as well. So there's different efforts sort of going on at play right now, but I think like the main general point here is that there is urgency now to transition to make sure that you're set with the new standards, and if those new standards change, you know what you're dealing with. So
Yeah, absolutely. I'll just add, you're correct that any information that has been captured and stored by adversaries, the reality is there's just no solution to that problem. Like, if they do eventually develop a quantum computer, they will be able to read that information. Now, it's not easy to do. I think few people have those resources, but
Yeah.
some people might. So yes, we need to adopt post-quantum cryptography far before quantum computers are available,
yeah.
And
that's also like why likely we would only have the resources to do that at like the national level, at a nation state level. So that's why the U.S. is so invested in being in the first country to have a quantum computer for that very reason.
So my question is about, you're competing with generative AI, right? Google's going to spend $85 billion this year on backbone infrastructure, Amazon spending 115, Meta spending 75, in infrastructure, not people, in addition to people. Wall Street over time is going to want a return on this $1 trillion investment over 3 years in this sort of closer term, generative AI. Is that good for quantum computing or bad for quantum computing? Because you get brain drain, there's real competition for power
Yeah.
that you guys need too. And is it bad for quantum computing that you guys have to come next because
Yeah.
we got to get a return on what we're spending now on generative AI?
Yeah, I will say I wish I had more time to talk about the differences and similarities of quantum and AI. Our Google team name is Quantum AI, and I think the way that we see it is that they are not competing technologies. They are fundamentally different hardware solutions, so they sit in different spaces. Where they are similar is that they're both being developed to help build things that can solve really big problems that'll help our industries. I think they're more so complementary in a lot of ways. For example, there's areas of quantum machine learning that we think quantum can help machine learning and machine learning can help quantum, and maybe we could chat about it more because I think we're out of time. But for example, in machine learning and AI, a lot of the sort of bottlenecks are around how much information we can process, as well as certain optimization problems in tensor networks, for example, and quantum computing can potentially really help solve those things. So I wouldn't think about it as competing technologies and rather complementary ones. Yeah.
I actually have a slightly different take, but I also we're out of time, so I'll give it in 10 seconds. I'll say it's complicated, but I would say in terms of enabling technologies, they are complements. You can use AI to improve the development of quantum computing. I would say in terms of end user applications, they're kind of orthogonal. They approach different kinds of problems. I think there's relatively few cases where they'll both be directly competing, but that is still difficult to say. And I will say in terms of talent and competition and scarce corporate resources, I would say there is actually some degree of competition there, and you could imagine some brain drain in both directions, and realistically, it would probably be going from quantum to AI, because
Yeah.
that does seem to be where the near-term money is.
Yeah. I mean, from Google's standpoint, we're investing in both because we think that they would each help one another, let's say 5 to 10 years down the road. If we have a quantum computer that can help our AI systems, and if we have the best AI, it could help our quantum computing system. So it's kind of hard to say whether they're competing in or complementary in the resources space as well, because they can potentially help one another.
Well, thank you all very much. That was really fascinating.
Thank you.
So once our brains recover from trying to understand quantum, we're taking a 15-minute break, and we'll be back here to talk about antitrust